Reducing uncertainty in atmospheric process modeling has far-reaching implications across various fields, particularly in offshore wind energy, which is the main motivation of this talk. Wind turbines in an offshore wind park disrupt the airflow and generate wakes, as depicted in these figures. Accurate modeling of both wind behavior and wake in the area of offshore wind park is crucial for cost reduction in the offshore wind industry. This importance has been recognized and addressed in the Work Package 2 of the EU project HIPERWIND. In this video, I and my colleagues aim to demonstrate how the use of observational data can reduce uncertainties in our modeling framework during a low-level jet event. We will also briefly discuss a realistic result obtained by coupling a wake model with the WRF meso-scale model. In this study, we utilized the weather research and forecasting WRF model, a complex system known for its chaotic behavior resulting from nonlinear interactions of physical processes. Our main goal is to reduce uncertainty in the WRF wind forecast, specifically during a low-level jet transient event. Low-level jets are characterized by local wind maxima, which impacts the wind turbine loads and many different aspects. They have positive and negative shear above and below this core height. Let's dive right into the study site, data, and the WRF model configuration. Our study area is around the Finnovan offshore meteorological mast in the southern North Sea. In the vicinity of Finnovan, we have Alpha Ventus offshore wind park containing 12 5-megawatt wind turbines. We use measurements we at Geophysical Institute collected between 2015 to 2016 during OBLEX F1 campaign. We deployed several instruments to measure ocean, atmosphere, and waves. In this study, we use sonic anemometer and LiDAR data. We have two LiDAR systems. One of them looking towards the Alpha Ventus wind park that is used for the model verification and validation, but the upward looking LiDAR is used for data assimilation, as shown in this figure and here as a result. It is noted that we need to develop accurate retrieval algorithm to estimate wind from the radial wind measurements of LiDAR. This figure shows the LiDAR data at different heights from 25 meter to 1,200 meter between 13th and 14th August 2015. In our approach, we utilize the WRF model with 3 nested domains featuring resolutions of 9 km, 3 km, and 1 km. Specifically, we leverage the results from the 1 km domain to provide boundary information for the large eddy simulation wake model, which I show end of this presentation. To reduce uncertainties, our first step involves accurately selecting and tuning parameterizations for microphysics, convective processes, planetary boundary layer parameterization, radiation, and turbulence within the WRF model. With these parameterizations in place, we proceed to perform data assimilation using wind direction and speed data from upward-looking LiDAR. Data assimilation, or DA, combines observational data with the WRF model to improve its accuracy by reducing uncertainties. In our study, we employ two types of DA: three-dimensional variational DA, or 3D VAR, and observational nudging assimilation, OA. 3D VAR aims to find the optimal model initial states to get better fits with observational data by minimizing this cost function. The first term represents the model error, while the second term stands for the observation error. To accurately estimate site-specific covariance matrix B is really crucial for this optimization process. The next method is the observational nudging, which, on the other hand, involves introducing an additional forcing term to governing equations of momentum, for example. This term and this method continuously adjust the model state towards the observations. While this approach is computationally more demanding than 3D VAR, it has demonstrated better short-term forecast in our experiences. However, it should be noted that observational nudging introduces non-physical terms which may cause artifacts in the model domain, but can be managed somewhat through careful implementation and interpretation of results. This figure shows the 10-minute average wind speed from upward-looking LiDAR in time and heights, as shown by the dotted markers here. These data points have passed the required quality criteria of DA before being used in the WRF DA system. The low-level jet core is observed on 13th August 2015 at around 1420 UTC with an approximate jet core at 290 meter height. This event persists for a few hours and is followed by another weak low-level jet at around 14th August around 8 UTC. Here I do not show the control run because there has been slight differences between control run and the results from the WRF with 3D VAR DA. Figure B, results of the 3D VAR, suggests that the WRF with 3D VAR over-predicts the wind speeds. The jet core for the first event is expanded over a longer distances and longer duration relative to what is expected from the measurements in figure A. Now, we use the observational nudging in the figure C. The overall agreement with measurements is greatly improved by employing the observational nudging. The model predicts very similar variation before, during, after the low-level jet event, and the remaining discrepancies are explained by the fact that a limited number of measurement points in time and space have been used for the nudging. In work package 2 of the HIPERWIND project, we have developed two multi-scale frameworks. In this video, I will focus on one specific specific methods of coupling between the WRF model using data assimilation and the Palm Large Eddy Simulation wake model. The Palm wake model is integrated with WRF through offline nesting, obtaining boundary information from the high-resolution WRF model with 1 kilometer resolution. With this multiscale framework, we analyze the wake characteristics within the Alpha Ventus wind park during this specific low-level jet event by reducing the model uncertainty, because our original model is not able to properly capture this event. During the low-level jet event, between 13th, 14th August 2015, under stable atmospheric conditions, you can observe the evolution of wakes in this video. Notably, in stable conditions, the turbulence induced by wake meandering or wake-added turbulence is significantly reduced, particularly in the near wake regions. Utilizing high-quality LiDAR data and sophisticated retrieval algorithms in data assimilation, we observe a reduction in model uncertainty. This reduction in meso-scale uncertainty has significant implication for wake modeling within and around a wind park across various atmospheric stability conditions. Here, stable condition more specifically. Our developed multi-scale framework enables accurate wake modeling, leading to improved understanding and analysis of wake dynamics.